Everyone to the final lightning talk, and we've got Gabor. I believe you're talking about effect ordering or something.
Yeah, right.
So let's find out more. Welcome.
Well, the title was just clickbait, so you come inside. Okay, so I'm from Nokia, but this is private fun. So, but here we have some, let's say, a university network for, let's say, England and Scotland. And this is a stream of synchronous data, unidirectional in some fibers with lasers and so on. And we can also put some meta information on the data stream, which can be checked in each hop. So in this case, we check the destination meta information, which is inserted at the node Dundee and checked in Edinburgh. And we find out that it's the same, so no alarms are activated. And also, there is a second feature. When there is an alarm, we have optionally the ability to cut the data stream and don't transmit it further, so that we can avoid some misconnections where data is transmitted in places where we don't want to transmit it. Okay, so in case we want to reconfigure a node, let's say Edinburgh, we can insert some command which corresponds to a transaction. And in this case, the configuration tree from before and after are compared, and there are some actions which fall out of this process. It doesn't really matter how, but it results in a bag of reconfiguration actions which, let's say in this case, change the destination comparison, the destination identifier, which is checked against, and also we turn off the cutting, which was active before. And in this case, when we now naively execute this bag of actions, then it could happen that because of the unordered nature of bags, that we first change the destination string, in which case the alarms go off, and we also, because of still activated cutting, we cut the laser, and this causes an outage in our data traffic. Okay, so the next action would be the deactivation of the cutting, which would reopen the data stream, and it would be transmitted on. So what we have is basically an unfortunate interruption of our data stream. This is not what we want, because we want an atomic execution of our bag, which should choose the best possible ordering. If we would have executed the actions in the reverse order, everything would have been very nice. Okay, so to restore this atomicity, we try to flag or tag our actions with corresponding semantics. And, for example, by using tagged I/O actions or such. And we can also add a new kind of objects to our bags, which I call catalysts, which are able to consume certain actions with corresponding tags and put them in a predefined order into this execution chain. So this little picture should show that two actions get ordered in this kind of template, in this rule. Okay, now how do we communicate these actions to our domain experts? Because every domain has its own special rules, and there are several people who know how these rules should be written. And in this case, we can, of course, write them down as Haskell signatures, as function arrows. Okay, and behind the scenes, we expect that there are some monadic combinators which do the work. These can be, of course, inferred, but the important thing here is that we have to write down the rules first. And in our case, to avoid this complication, which I have shown before, we have to write two rules. And this gives us a shallow embedding, but in our case, since the bags don't always contain all the necessary actions to saturate these errors, we sometimes have to saturate along the codomain of our arrow. Okay, so the action should end up in this place. So we have to, we want to obtain this residual catalyst in our bag. Okay, so we try to apply arguments in the codomain of our function arrow. And this normally is not possible because Haskell has type erasure and deletes all the types from runtime. But new feature of GCC gives us this typeable type reflection framework, which allows us to do exactly this. It gives us back the typing to values at runtime. And for that, we can differentiate for every type. We can get a type representation, which we can analyze and pattern match against. For example, we can find out function errors or type constructors with applied maybe on several arguments. So let's have a small type family which does elimination of a certain type from a chain of function arrows. And we would write it like this. Who knows the preludes delete function? Probably everybody. Just throws out from a list, for example, an element and shortens the list. Here we shorten the function arrow. If the type matches our domain, then we just return the codomain. Otherwise, we push down the elimination down the chain of arrows. Okay. Now, let's assume that actually the type v, a value v matches the type of some argument of f. And in this case, we could write such a function. Find out whether the domain matches with the type of our object. In this case, apply the function. Otherwise, construct a new function, which we give back, but we apply our recursion down in the codomain. Of course, this never will work because first, it is not total, so our assumption cannot be really respected. And the second thing is that because of type erasure of Haskell, no one can write such a function, matches codomain of. And the third thing, of course, that it won't type check. But it's a skeleton for our future implementation. Okay, let's try to make it total. Normally, we just decorate the result with maybe. But in this case, the application case works fine, but the other case won't work at all because you would have to need to implement such a function with this signature, which is simply not possible. You can try it at home, it won't work. Okay, so maybe we can find a better idea. So what about putting the maybe just a position to the front and return a transformer which takes some function type and eliminates a value type from it and gives that back. In this case, we hope to use composition on the result of our recursive call with something, and then we might have a result. Okay. In this case, however, let's go back a bit. We get an ambiguity because f is not mentioned in the arguments. In this, to get this problem solved, we pass in the type representations of our f, the type representation v, our v, and get back a maybe transformer. Now everything falls in place, and we can analyze whether f has a function arrow as a type representation. We can test the equality of our value type representation with the domains type representation. If we find out that they actually match, we get a proof for the compiler, for the type checker, that we can actually apply our value to this function, to this in the domain position. If we don't get anything back, then we can try to run the recursive pushing down the algorithm into the codomain and return that. Of course, this still doesn't work, so we have still an error. And the error says that that this equality cannot be deduced by the compiler. So, question is, why does GHC says that? Because the second clause of our type family exactly says this, what is missing. So it should be possible to figure this out by GHC, but unfortunately this is not the case. A case statement here, this case statement doesn't know that the first case is taken when not taken when going in the second case. So the inferred information by which it would be necessary to resolve the type family is simply not available. Okay, what can we do? We can take a bitter pill, yeah? And I've redacted this so that you don't suffer mental pains. Okay, so what we can do, we can simply write a faking function, which I call postulate, and extract this type equality by force to convince the type checker that everything is right. Okay, but of course, nobody should be forced to use this technique. What about witnessing the distinct lines of our type family and having for each line or each clause an own constructor which we can pattern match against. So in this case, we find out, yes, it's a function. We call a reification of this type family as and obtain a witness, which of the clauses was active, and then pattern match against them, and in this case, everything works out. So this is done by my relatively new HaskellX uploaded library, which generates such GADTs which capture all the information which is encoded in the clauses of the type family. And also there is this refi-lm, for example, for each type family. Here I use it, which obtains a witness, so which gives us a runtime analyzable result which clause of the type family would be active. This way, we almost resolve our problem. The only thing that remains to be done is to construct also return a type representation of an eliminated, a residual catalyst, and then convert that to a typable, which is possible by this library, type reflection. There is a function for that. And then we can construct again a residual action, put it back in the bag. What have we gained? We have a simple DSL, which captures rules for ordering effects. The result, after we run this process and obtain a fixed point in the bag, after all reactions have taken place, we know that every relevant and sequenceable or necessary to be sequenced effect has happened or is sequenced in the right way, so that every remaining action in this action bag can be executed in parallel. That means we can immediately saturate our multi-core CPOs. And yeah, that reduces our latencies for the execution. And yeah, that's it. Thank you very much.